In the past two videos, I've talked about how when the magnetic flux going through a circular loop changes, how that would induce a voltage in the loop. Now the question I want to talk about in this video is which direction is this voltage induced in? Is it this way or the other way? So let me think of a loop. Let's say I have a loop here. Now I need to show this in try to draw this in 3 dimensions. So I'm going to make this part of the loop thicker. Make this part of the loop obviously thicker. So this is supposed to mean that this side is nearer to us and that other side is further from us. I'm going to draw 2 such loops. Otherwise this side, this is the side that is nearer to us. That side is further from us. Next, I'm going to imagine that there is a magnet. Okay, there is a magnet. Draw a little bit further away. There is a magnet here, the North Pole here, the magnet here, the North Pole here, and I would move this magnet towards the coil. Now, from what we understand of electromagnetic induction, as I move the magnet closer to the loop, assuming that this is made of copper, so that it can conduct electricity. As I move the magnet nearer to the loop, the magnetic field going through this loop will get stronger. And that means that the magnetic flux through the loop would increase, would change. And therefore, a voltage must be induced around the loop. And therefore, since it's a continuous loop, there must be a current. So the problem now is to determine the direction of this current. Now there are only 2 possible answers. Okay, either the currents go this way or it goes that way. And actually there is a simple way to find out. Let me start with this possibility. Suppose that the current goes this way. So think about the magnetic field that is produced by this current. Now we've seen this in a number of videos ago when I talked about the magnetic field pattern, when I sketched that magnetic field in and around a flat circular coil. If you look back at that video, you'll see that the magnetic field from a flat circular coil like this looks not so different from the field that you get near the pole of a magnet. Kind of looks like this, just like an extremely short magnet or extremely short electromagnet. Okay, and if the current is going this way, we can determine the direction of this field using the right hand thumb rule. What we would do is we would maybe stretch out our left hand, our right hand, just flat, stretch it out flat. Maybe put the side of our left hand, our right hand near the loop, and wrap our fingers round in the direction of the current, then the direction of our thumb would point in the direction of the field. So therefore the field points in this direction. In this case. Now, if the current is going the other way, the field would point in the opposite direction. Let me draw that too. So in this case, the current points here. As I said, this is like a very short magnet or electromagnet. So if the current is coming out in this direction, it means that this side is the North Pole and that side is the South Pole. This side is the North. That side is the North Pole and this side is the South Pole. Okay. If you look at the top figure, the first possibility, I have a North Pole here on this side, and I have a North Pole of this magnet which is trying to get closer to the coil, which I'm pushing closer to the coil. And we know that like poles repel. So as I try to push this towards the coil, towards the loop, the North Pole that is created here by the current would repel this. Okay, so there's a repulsion, there's a force of repulsion here. North Pole and North Pole, the two poles repel. Now if you look at this possibility, I have a South Pole on this side and a North Pole coming in, and opposite poles attract. So in this case, they attract. And it is this difference that would allow us to tell which of these is correct. If you think about this, in this case, if they repel, it means that in order for me to push this magnet towards this loop, I have to do work. I have to do work against this repulsion, because this North Pole is trying to push me away. So I must do work to push this magnet in. Okay, so in this case, in order to push it in, I must do work against the repulsion, against this repulsion. Okay, so that's the effects of this possibility. But in this case, because they attract, I actually don't have to do any work to push in. Right? Assuming that I put this, say, on a very smooth table or very oily table, the attraction would just continue to pull the magnet towards the loop. It would just continue to pull the magnet towards it. So here, I don't need to do work. Okay, I don't need to do work because the magnet is attracted, because there is okay, magnet moves under the attraction. Okay, now if we look at these two, think about these two in terms of the conservation of energy. In both cases, the current here is generated, is induced because this magnet moves towards the loop. Now, the electric current is electric energy. Okay, so there is electric energy here is being generated. Now we have to ask the question, where does this energy come from? In the first case, because I have to do work to push against the repulsion, to push this magnet against the repulsion, I have the answer. The electric energy comes from the work done down here. So let's do work against the repulsion, and this gives the electric energy. This gives the electric energy. So it makes sense. Okay, the work that I do, energy that I use to do the work is converted into electrical energy. Energy is conserved. No problem. How about the second case? In the second case, I don't have to do any work. I just let go. Alright, at first there's no current, right? But I just let go, magnet moves towards the loop. Electric energy is created. So electric energy is created out of nothing. Energy is created out of nothing. Okay. Energy created. This is electric energy. So electric energy created out of nothing. And this is the part that can't be right, because we know that energy is conserved. So this must be wrong. Therefore, this direction must be wrong. Okay, and that must be the correct direction because we must do work to get the energy according to the law of conservation of energy. Okay, so this is correct because it obeys the conservation of energy. So we have a very important result down here. We have a way to tell the direction of this current, that is induced, or the direction of the voltage, because they would be the same. Alright, if the current goes in this direction, the voltage also goes in this direction. So we have a way to tell the direction of this current and voltage. And the way is this. The way is that the direction of the current, okay, must produce a magnetic field that opposes the magnet, alright, or opposes the incoming field, so that energy can be conserved. So whatever the direction of this current is, okay, it must be in such a direction as to make me do work if I want to create it. So in this example, I've talked about having a north pole pointing in this direction and pushing it towards the loop. I could also turn the magnet around and have a south pole here instead. And when I push the south pole towards this, I can use the same idea. Alright, if I have a south pole here instead, then that must be a south pole to repel this, which means that the current must go in the opposite direction. Right, so I'll write down a few of these possible cases in a moment. But for now, let me summarize these results. Summarize this result. Okay. The result is this. The induced current must be in a direction So okay, it's a bit tricky to describe. Let me try again. The direction of the induced current must be such that it opposes the change that produces the current. Okay, this, if you're saying this for the first time, it's going to be a bit abstract. It's going to be a bit abstract. And the most abstract bit of this is probably these two words, such that. What do you mean by such that? It is not as if it is the direction of the current that is opposite to the say the motion of the magnet, right? Such the change, right? The change is another abstract part of it. So it's not as if the current direction is directly opposite to say the motion of this magnet, because the magnet is moving along this direction, but the current is going around in circles. Alright, so it's not those two directions that we're talking about. So what we're actually talking about is basically what I have been describing just now. What this means is that the direction of the current must be such that the such that here means the current such that the current produces a magnetic field, and it is this magnetic field that opposes, say, this magnet in this case. Okay, so that's usually what the such that here means. It's a rather odd way to say it, but it is the reason why this such that is used is simply to make this sentence shorter, but unfortunately that means that it is hiding an important part of the idea. So the current must be such that means that the magnetic field, the such that here refers to the magnetic field of the current. Okay. Current must be such that means that the current would produce this magnetic field, and this magnetic field must oppose the change that produces the current. The change in this case is just the magnet moving towards it. So why not just say the magnet moving towards it? Now, there is an important reason why we don't want to be specific here. The reason is that this is not the only way to induce moving a magnet with a north pole on the left side towards the loop is not the only way you can cause a change in magnetic flux. You can induce a current. Like, for example, another possible way, as I just mentioned, was that I can push the south pole towards this instead, or I can pull this magnet away. We can already think of 4 possible combinations. I can either push it towards here or pull it away. Either way, I would cause a change in flux and therefore induce a current. I can have the north pole on this side, or I can have the south pole on this side. So altogether, there are already 4 possible combinations. And there are other ways to produce a changing flux here as well. For example, I can use an electromagnet. In other words, I can use another current instead of a real magnet. So there are many possibilities, which is why we use the word change. So the change here means you can have a moving magnet, and that already can have many possibilities. okay, like left, right, north, south, okay, moving magnet, or I can have a changing current, maybe another loop, another changing current nearby. So a nearby changing currents, and that changing current can also be done in different ways. Okay, so let me finish up by writing down the name of this law, because this has been this has been stated as law, and it is called Lenz's law.